Okay, so here's where we are now. We finished section 6.1 yesterday. Moving on to 6.2, let me just remind you, so we're talking about a new category of differential equations. These are sort of the matrix notation for them, but don't forget these are systems, right? This is just a shorthand notation for an entire system of differential equations. A coupled linked system where there's y2s in the y1 equation, etc. That's what makes it hard. Like we did in chapter 4, remember there's these very strong analogies between how things developed in chapter 4 and how things are going to play out in chapter 6. We talked about the theoretical framework, the abstractions, the theorems, in the first section of the chapter, and now we move on to consider the homogeneous case, right? Section 4.2, we talked about homogeneous differential equations, linear, constant coefficient, etc. So homogeneous, again, is going to be the next thing that we're going to consider. That's actually going to, as it turns out here, going to take us 2 sections here in chapter 6, because there are kind of subcategories inside of this case that we have to worry about. Turns out, we'll see why momentarily, diagonalizability matters unexpectedly, but it does matter. So anyway, after we finish talking about homogeneous equations, then just like in chapter 4, we will move on to considering non-homogeneous equations. And of course, we remember that particular plus homogeneous gives you general. Right? So same basic strategy from chapter 4. Okay, so we're going to start homogeneous, so there's no sort of stuff on the right, if you will. But we are furthermore specifically going to consider the case where this matrix is diagonalizable. Because it gives us a powerful tool to be able to solve these problems. Okay, and we'll worry about the non-diagonalizable case later. Okay, moving along. Oh, of course, constant. This is a constant matrix, sort of analogous to the constant coefficient case that we thought about in chapter 4. Okay, so what do we do? Why does it matter if the matrix is diagonalizable? Well, short version, in chapter 5, what we saw is that if a matrix is diagonalizable, then a change of basis makes life good. It makes it easier to represent the linear transformation. Well, if you think about it, just kind of at a glance, what is this matrix doing? This matrix here is relating to vectors. It's like it's a linear transformation, right? It is a linear transformation, right? So we have, what we have here is, you can get bogged down in the coordinates and stuff, but a simple way to think about this is I've got this vector called y, and I've got this other vector called y prime, and I would like for those two vectors to be related by a linear transformation. And if I can simplify my understanding of that linear transformation, stands to reason it might be an easier problem to solve. Okay, so that's what we're going to hope for. We're hoping that a change of basis, just like we saw in chapter 5, will help us simplify our system of equations. All right, now does it? Let's experiment. Let's see what happens. So suppose we have a diagonalizable matrix. Keep in mind that's what diagonalizable means. Different points of view, of course. A can be diagonalized by a representing it with respect to a different basis, or here I'm writing it as conjugations, right? Another way to say it, a matrix is diagonalizable if there is an entire basis consisting of eigenvectors, right? Several different ways of saying the same thing. This is how I'm going to write it here. Okay, if that's the case, plug in the diagonalization. Seems like a natural thing to do, right? And let's look at this new equation. Is this better? Not clear, right? It certainly doesn't. If anything, it looks kind of worse. There's 3 matrices now instead of 1. That's not good. Here's the beautiful move. This matrix here. Move it over to the other side as a P inverse, of course. You get this equation. Then we do a substitution. P inverse y, let's call that z. And notice that our equation now has it's at least changed. I'm going to say simplified, but it's at least changed. Right now, we're looking at one of these first order systems of equations. At least now the matrix is diagonal. Previously, our original form of the equation, the matrix was not diagonal. But by this change of basis, now it is diagonal. And the question that comes up now is, why does this matter? Why do we care about the fact that this matrix has become diagonal? And the answer is, write it out in coordinates. Right? We've got this nice handy matrix shorthand, and that's convenient and all, but let's expand it out and see what we're really looking at inside of there. This is what that system now looks like. Right? So the first equation is z1 prime equals, and we're going to look at that D matrix and look along the top row, and those are the coefficients that we'll have for z1, z2, z3, z4, etc. Being diagonal, of course, we just get the one term, etc., etc. And what's fantastic about this is these individual equations are easy. All right, look at that equation right there. That's a really easy differential equation. That's a Calc 2 differential equation. It's just the natural growth equation. Right? Let's look back at our original problem way back. Too far. Our original problem here, we were looking at these. We're thinking about homogeneous. Looking at these, the big problem was that the y1 equation, for example, didn't just have y1s in it. It also had all these other terms involving other functions that I don't know yet. Right? There was yn's and yk's, etc. in my y1 equation, thus preventing me from solving it. Everything you might recall. Oh, what did I think I just hit my. Oh gosh. Sorry. Okay, hopefully I can just not touch it. That wire, I guess, is very delicate. Okay, so in this situation, you remember this little hand gesture that I did? Everything is kind of intricately linked and kind of tied together. Everything, the y1 equation's unavoidably connected to y2, which is therefore involved with the y2 equation, which is connected to y3, which is connected to y1, and everything is just in everything else's business, right? And this have this nasty rat's nest of a problem. What we have here now, going over to this, is that rat's nest has completely untied, right? There's just z1 in that equation. There's no z2s in the z1 equation. There's no zn's in the z1 equation. It's just there by itself. So that equation, let's do it like this. This equation is completely independent of that equation, which is completely independent of that equation, which is completely independent of that equation. So this is what we call decoupling. The idea being that coupling means two things that are linked together. These equations are no longer linked together. How we doing? Everybody on? Ever see how wonderful this is? Details to come, for sure. Okay. All right. Okay. What made this all possible? How did we get this decoupling? Ultimately, we got this decoupling because this matrix is diagonal. How did we get that matrix to be diagonal? Well, ultimately, because this matrix A is diagonalizable. So this assumption that we made at the start here, that we're looking at diagonalizable homogeneous systems, that's what makes this argument go through. Alrighty, so let's worry about details. I guess I've already said this, but let me say it again before we go on. Don't forget the substitution here involves this matrix P. Where does P come from? P is it's the matrix in the conjugation. It's a change of basis matrix. It's the change of basis that diagonalizes the system, and don't forget that means that the columns are eigenvectors, right? So eigenvectors are still involved in our story here. eigenvector, different point of view. Eigenvectors are what has allowed us to simplify this problem. And just to sort of capitalize on that, this basis of eigenvectors, in the same way that it simplifies linear transformations in Chapter 4, now, ultimately, is what allows us to simplify our system of equations in Chapter 5. Okay. All right, so now let's get involved in details. Let's look at these equations one at a time. Natural growth. Calc 2. Right, these equations are easy to write down solutions to. Here they are. There's a solution to the first equation, second equation, et cetera, last equation. Yawn. Right? Now, okay, these are solutions to the individual coordinates. From a, you might say, a calculus standpoint, maybe this is a satisfactory way to write the solutions, I guess, maybe, or something. But remember, we're going to take a linear algebra point of view on this. So how can I rewrite this as linear algebra? Well, for one thing, I can take these solutions and I can assemble them into a general solution vector. Right? Remember this, the idea of the z equation is that we have a z vector of functions. So here they are. Again, just Calc 2. Right? Now let's take a linear algebra point of view on this and note that this can be rewritten as a linear combination like that. Now, you got to think through the coordinates. This thing right here is e to the lambda 1x. Oh, sorry, bad writing. Lambda 1x in the first position, and then all zeros after that. And you can see then that multiplying by c, by c1, is what sort of makes this show up in that first position. Okay, so it's just linear combinations by coordinates. Okay. That allows us to conclude that these vectors, these vectors are a fundamental set of solutions. See, now we're talking linear algebra language. We have the general solution is written as a linear combination of our basis vector. So this is a fundamental set of solutions. There's our fundamental set of solutions. It's nice to have everything written as a fundamental set of solutions. Again, the language of linear algebra, very useful. Here's the downside. Of course, we're actually not quite done yet. We solved this z equation. The z equation was motivated by, hey, look how much more desirable the z equation is than the y equation. But it remains that what we're actually interested in here is not the z equation. I am not originally interested in solving for z. I want to solve for y. Right? So a classic mistake that I'm sure you all remember from Calc 1 days, you do a substitution and an integral and, do the antiderivative and then forget to plug back in and write your answer in terms of the original variable. So here we are. I want my answer for what is y. Z was a tool. Not the original question. So what is y? Well, don't forget, in our substitution, z is p inverse y. Otherwise, I might say y is pz. Right? So we've just got to rewrite then y equals pz. I've got to take these z functions, plug these in here, and that'll give me my y's. Okay, and that's, as it turns out, pretty easy to do. So these scalar valued functions are going to come along for the ride. These are still here. Here you go. They're there and there. Those scalar functions don't do anything with them. They move inside and out of a matrix multiplication, no problem. We are looking to multiply here P times the z vectors, the vector portion of which are just standard basis vectors. Look at this. My y's are just matrix times standard basis vector. A matrix times a standard basis vector just picks out the appropriate column. Look at our matrix. Our matrix is full of eigenvectors. The columns of our matrix, just eigenvectors. So when I multiply the P matrix times the Z vectors, the resulting vectors that come out, just the eigenvectors. How are we doing? Pause for questions. Anybody have any questions about that? All right. Okay. So there you go. There's our answer. Now, good news. We've solved this first example of a diagonalizable matrix system, right? So you see a process here. We have this process of, diagonalize, substitute, and then solve the decoupled system and then plug back in. That's our sort of big picture of our process. But here's the thing, there were very few assumptions that I put on this question in the first place. All I assumed is, hey, that my matrix is diagonalizable. What that means is that this calculation that I've done here, I didn't just solve one question. I've just proved a theorem. Right? This solution that I've written down here, this will be the solution whenever the matrix in the original system is diagonalizable. And here's the theorem. Really, really convenient theorem. Crazy convenient. So, if you're looking at your homogeneous diagonalizable system, gotta be diagonalizable. Don't forget, diagonalizable means you've got as many eigenvectors and eigenvalues as you could possibly hope for. So let's suppose that here's your eigenvalues, and that correspondingly here's your eigenvectors. Remember, alternative formulation of diagonalizability. You have all your eigenvectors. Okay, well then it becomes a plug and chug. The eigenvalues go here. The eigenvectors go there. So because the matrix is diagonalizable, because you have eigenvalues and eigenvectors, there's your fundamental set of solutions. It always works. Isn't that nice? Anybody have any questions about this? Okay, so I can now close a loop. There was I wrote down a set of solutions to this system of equations. You might recall this is the first, back in 6.1, I wrote down here's a system. Let's suppose the matrix is that. And without any discussion, I just immediately said, hey, here's a couple of solutions that I just pulled out of thin air. Right? With comments about how, we'll worry later about where these come from. Let's worry about linear algebra right now. I wanted to make a dimension argument and say, look, we know we have a two-dimensional solution. Here's two solutions. They're independent. Linear algebra, linear algebra, linear algebra. We're done. Right? That was the focus at that time. But it did remain that eventually I was going to have to show you where these solutions came from. So here we are. The way it comes is this matrix. We've already previously solved for the eigenvalues and the eigenvectors, and note that just as in the above theorem, I just plugged in eigenvalues there, eigenvectors here. Done. That's where they came from. Everybody good? Okay. Surely someone's got a question? Is everybody, if no questions, that's fine, but feel free. We're doing okay on time. Okay. All right. So what if the eigenvalues are complex? Remember, this is a story that happens sometimes. It's a little annoying. But say this matrix. Now that matrix is diagonalizable because we have three eigenvalues and three eigenvectors. A bunch of details for how to find that. Don't forget how to find eigenvalues and eigenvectors. But just like before, you can take those eigenvalues and stick them in the appropriate places and the eigenvectors and put them in the appropriate places. right? And there's your fundamental set of solutions. We have our usual problem, though, and that is that this fundamental set of solutions is undesirable, right? The question came to us in this form where everything was real. Imagine, you've got some real world scenario with real masses and real springs, or who knows whatever the system or the actual physics problem is. But you come with a real problem, and then the person who answers your question comes to you with complex solutions, right? What is this? We're in the real world, not the complex world. So we would like to be able to replace these, or trade, perhaps, these complex valued solutions for real valued solutions. Specifically, these two here that are complex valued, we'd like to swap out for real valued. Good news, linear combinations do it just like they did in chapter 4. So all I'm going to do is take this complex valued solution, I'm going to go through this algebra with y'all momentarily, so bear with me. But I'm going to identify how to write this thing as a real part plus an imaginary part, and then we're just going to say, well, the real part is also a solution. That's good. And the imaginary part, throw away the I, the imaginary part, also a solution. There's my then two real solutions. Okay, so details. How do I deal with this function? How do I separate this out into real and imaginary parts? It's totally analogous to how we did it in chapter 4. Notice what we have here is a product of what I'm going to call a polar form complex number and a rectangular form complex. Okay, it's a vector, whatever. But polar, rectangular. And it's just not convenient to multiply polar times rectangular. So let's first thing turn everything into rectangular form. I will also first thing, if y'all don't mind, take this e to the x. Let's get that out of the way. Right? All that remains then is the e to the ix. So I'm going to write in rectangular form. Then there's this rectangular vector, which I will just leave as it is. Now I've got, this is much nicer, rectangular times rectangular. And that's something that is just a matter of just multiplying it out. Right? So real quick, let's walk through the algebra on that. The e to the x along for the ride, of course. Okay. Let's look for the real part. Real is going to come as real times real. It's also going to come as imaginary times imaginary. Right? Don't forget the minus sign. But real times real is real, imaginary times imaginary is real. That gives you your total real part. And then likewise, if you want to know your imaginary part, well, real times imaginary gives you imaginary, and imaginary times real gives you imaginary. So it's really just like in chapter 4. It's just that now there's, a vector involved, but one component at a time. It works pretty much the same. How are we doing on this? Everybody good with this so far? Okay, so reminder of what we were doing. We didn't like these two complex valued solutions. Note that they are conjugate to each other. Just like in chapter 4, we replace a conjugate pair of solutions instead with real and imaginary parts, that and that. So that's what I use instead, like so. And our original fundamental set of solutions turns into this, which is a real fundamental set of solutions like we wanted. Everybody happy? Alrighty. Okay, so what about the non-diagonalizable case? The diagonalizable case, I mean, it just works out great. It always you always plug in the conjugation, do the substitution, take the decoupled equation, right? Celebrate a little because it's decoupled. Take the solutions to that, plug them in. You always get the same structure of answer. It's just eigenvalues and eigenvectors. It's very plug and chug. A quick reminder, though. Let me make sure to remember that in this class, it's not just a question of can you get the right answers down at the bottom of the page, right? So they'll take away from that discussion that we made. Yeah, sure, be able to execute the theorem. Right, of course, absolutely. But make sure you understand where the theorem comes from. Make sure you understand all the steps in the process. We are not just going to ask you on the exam to hear, plug in the answer, right? Because I know y'all are really good at that. Okay. All right. So what do we do with a non-diagonalizable case? We could, for example, try to do the same thing, right? It's not diagonalizable, but every matrix is Jordanizable. Jordan form is a consolation prize. It's close to diagonal. Got a lot of zeros in it. Zeros are good, right? So hey, let's even though it's not quite going to work, let's see where we get anyway by plugging in the Jordanization. We'll play the same game. We'll take this matrix here. We'll move it over to the other side. We will then look at this equation and make a substitution that P inverse Y we'll call Z, just like we did previously. The equation then turns into that, and it's not decoupled because this isn't diagonal, and so there's going to be some of this variable in that equation, and it's just not a perfect answer. But it turns out this is still pretty darn useful, and let me show you how. It's easier to see by example. So here's such a case. This is a non-diagonalizable matrix. Here is the Jordanization, if you will. Y'all can just take this as a given that this is how to Jordanize. So keep in mind what that means. I think it's important to remember that here we're representing a transformation with respect to the standard basis. Here we're representing the transformation with respect to our Jordan basis. That means that this matrix has to be change of basis from V to S. Therefore, that matrix has to be the matrix whose columns are our Jordan basis vectors. That means that this is our Jordan basis. All right, so remember we talked about that back in chapter 5, how to look at a Jordanization or diagonalization and think in terms of representing transformations with respect to bases, and therefore identifying where, is it on the left or on the right, where as columns do you find the relevant basis. Okay. All right, so there's our Jordan basis. Please don't just rely on, I see that there's an inverse here, so that means this must be P inverse, right? You never know. A problem can come up very naturally in such a way that it just, the conjugation is written in the way that seems backwards, right? So it could be that what if the matrix had been given as some different A matrix, and suppose it was, inverse there, right? Well, then we'd have to invert this matrix, right? I mean, it remains unavoidably the case that if this is J, then that means that this would have to be P, and in order to find the Jordan basis, then I would have to find the inverse of that matrix of seemingly friendly numbers, right? So you can't just assume. So be very careful with that. Okay, anyway, here we're going to take that part. Okay, so doing this change of basis above, we get, I was just there, we get Z prime equals J Z, this being our J matrix, and therefore the system is this. Now you can see right here, it's still not decoupled, right? There's still, I mean, it's not as horrible of a mess as it had been at the beginning, but it's still, there's a couple of little tangles in there, right? I mean, there's Z3s in my Z2 equation, there's Z2s in my Z1 equation. So the good news is, the Z3 equation is fine. I can solve for Z3. Nothing else but Z3s in my Z3 equation. Then, once I've solved for Z3, I can plug that into there, and I can solve for my Z2. And then once I solve for Z2, I can plug that into there, and I can solve for my Z1. All right, so this process is called back solving, because you're kind of working your way backwards through the system. And it's a little tedious, but it works. It will get you there. Everybody see the idea? By the way, I claim that when you Jordanize, it will always be back solvable. Not hard to persuade yourself of this. I mean, ultimately what makes it back solvable is, if you will, that sort of below the diagonal it's all zeros, and of course that is one of the features of Jordan form. Okay. All right. Okay, I'm going to do some of this algebra just because I feel like we should do at least one. It is kind of tedious though, right? So you be prepared. This is one of these situations. I mean, I hate to say it, but there are situations such as this one where you can't just, bypass all the effort. Sometimes you gotta get your hands dirty and take a deep breath, plow forward, and I'm sorry. So anyway, here we go. Okay, let's start with our Z3 equation. Here it is. The Z3 equation is that natural growth. That one was easy, no problem. Okay. Don't forget, we're going to take our Z3 that we just solved for. We're going to plug into there. That becomes the G, if you will, right, in our second equation. The second equation then becomes this. And that is a little annoying because it's non-homogeneous, right? We've got Z2 prime is 4Z2, but then we've got this other function of x. So we've got to play this whole particular and homogeneous game. Notice the homogeneous part is easy to solve. The homogeneous part's natural growth, so that's a freebie. To find a particular solution, well, this is an undetermined coefficients deal. Section 4.3. Make sure that you remember all the little details of how to do section 4.3. I claim, in fact, that there is an unfortunate coincidence in this equation. Let me walk you through that. Where does the unfortunate coincidence come from? Well, our characteristic polynomial is lambda minus 4. Right? Looking at the G, our R, our magic number, as you recall, A plus BI, is 4. And is this a root of that, we ask? And sadly, yes. Yeah? Everybody on board? So, because we have this unfortunate coincidence, we take our naive guess. Now, of course, looking at the form here, looking at that form, you would sort of naively guess that, just a multiple of e to the 4x. But because of our unfortunate coincidence, we've got to add in this extra factor of x. Yeah? All right, details. And it turns out your undetermined coefficient is this. And so your homogeneous solutions, let's see here, homogeneous plus particular gives you that. So, like I say, a little bit of effort that goes into that. Well, okay, I'm going to let y'all read through this third one. It's more of the same. It's a little bit uglier, right? But it's just details. Look at the characteristic polynomial. Look at the magic number. Note that there is a unfortunate coincidence. And go through and find your particular solution. The homogeneous solution, of course, is again pretty straightforward, right? And then particular plus homogeneous gives you your Z1. Make sure to read through those details. Make sure that you are proficient in cranking out this kind of details because, well, that's what this is. Okay. Yeah.
How quickly do computers do this?
Oh, I don't know.
It's like it's obviously like it's more computationally intensive than something that's like diagonalizable. And
Yeah.
It grows pretty quickly in magnitude of difficulty.
Yeah, I do have a faster way to answer these kinds of questions. I'm going to show you later. The faster way is more sophisticated, and I'm going to show you anyway. And you're allowed to use it, and that's fine. And that might be what is ultimately simpler. But in day in and day out, right? But still, I want you to know what this process is. Not that you'll necessarily have to do it on a regular basis. Computers keep getting smarter every day, so. I don't know what the actual state is on that though. Yeah. Anybody else? Okay, so long, tedious process, but notice we found Z3. Here, let me get rid of this junk here. We found Z3, and then we found Z2, and then now we have found Z1, and all together then. There they are. We solve for Z3, then we solve for Z2, then we solve for Z1. You write those down, and this is our Z solution vector. Now, note my indenting here. I indented this way on purpose because I wanted these terms to kind of line up, right? Because unavoidably these constants are the same constants. And then you can see I'm going to try to rewrite with the parentheses and everything. Likewise, these are the same constants. So, note we have here a linear combination we have a linear combination there of these three vectors, which I rewrite like that, then as our fundamental set of solutions. Oh, I should zoom back in. Yeah. Everybody good? That's our fundamental set of solutions. Wait, that's our fundamental set of solutions for the simplified system. That's those are the Z's. We don't want Z's. We want Y's. Again, same story, right? So again, we have to recall that each one of these Z's, you've got to multiply by the P matrix. Keep in mind, P has columns that are all eigenvectors, and in doing that multiplication, the Y's that you get are these. Now again, there's some non-trivial, it's just matrix multiplication. It's not that big a deal, but there's a certain amount of, tedium in writing that down. So think through, make sure that you go through those little details yourself as well. All right. Any questions? Okay. Right. So a quick comment about Jordan form. So you will recall that I started this example with, hey, here is the free arithmetic, no cost to you, that represents the entire Jordanization of this matrix. At which point it would be reasonable to complain, yeah, but we don't know how to do this. Right? So, it's fine for me to pull a rabbit out of a hat here, just, in the lecture notes, but in your daily grind, how are you going to go about finding a Jordanization of a matrix? We don't know how to find Jordan bases. You know how to diagonalize. Diagonalize just means finding eigenvectors, and y'all know how to find eigenvectors, but how do you find Jordan basis vectors? As a general method, we are not going to talk about that in Math 216. It's just a little too hard. There are some special cases in which certain conditions are satisfied, then, in fact, yes, you can go through and you can find Jordan bases. I used to teach that in Math 216 in certain special cases. And there are some old exam questions that have, students going through and doing that process. Due to how packed the course still is, really, but certainly was more back in those days, I've removed that from the curriculum. It's not in the book, by the way. It was always a supplemental thing. So anyway, so that's gone, so y'all are not responsible for that. I'm going to send y'all an email noting a specific example of this kind of question that I'm talking about. Old exam questions that have students computing Jordan bases using a method that y'all are not responsible for. So I'll have that email to you sometime in the next few days. Okay. Just to be clear, though, what you are responsible for is if I give you some arithmetic like this, from this arithmetic, you are perfectly capable of being able to identify a Jordan basis. Specifically, the argument we made previously by thinking about what bases are these matrices doing business in, and our punchline was that the Jordan basis consists of those columns right there. Okay. All right. So that you got to make sure that you're proficient with. Okay. Okay, but still, day in and day out, how do I find a Jordan basis? What if it's, convenient arithmetic is not given to me? And good news, computer algebra systems can do this. It's no big deal. Here's how you do it in MATLAB. I'm sure it's a different notation in each computer algebra system. So, in practice, yeah, that does a pretty good job. Okay. One thing to keep in mind for your consideration. The resulting Jordan basis, which of course will be, Jordan basis will be the columns of this P matrix, right? The Jordan basis is not unique. There are multiple Jordan bases for the same matrix that will result in the same Jordan canonical form. So just keep that in mind. I mean, in other words, if you use MATLAB and you use Python or whatever to find Jordan, if your Jordan bases disagree, don't worry about it. Probably fine. Okay. All right. Okay, we're doing well here. So let's move on to a special case, 2x2 matrices. So, again, keep in mind we're considering the non-diagonalizable case. If it's diagonalizable, we have a magic formula, crushes it, right? Every single time you just diagonalize, plug in the conjugation, decouple, solve, convert, right? It's always works. So, 2x2 though, if it's non-diagonalizable, here's the nice thing about it. There is only one Jordan structure. So, if someone says, or if you find by attempting to find eigenvectors, if you find that your matrix is non-diagonalizable, even though you don't know the Jordan basis, you do know the Jordan form. It's going to be this. Okay. All right. So by way of some details that we don't need to worry about, here's a nice punchline. This first vector we know is an eigenvector, right? Jordan block, first column, all that business. We know that first vector is going to be an eigenvector. The second vector, we don't know how to find it. And here's the nice punchline. It doesn't matter. Pretty much pick any vector. It's going to be fine. All right. Now, that does not mean that you will find a Jordan basis by picking any vector, but it does mean that by picking any vector, all right, so again, eigenvector here, pick any vector that you like. I mean, obviously don't pick 0. It's got to be a basis. Right? Obviously don't pick a multiple of V1. That wouldn't be a basis, right? But any other vector that makes a basis, and when you use that new basis to rewrite the matrix, the resulting matrix is upper triangular. Now, it's not Jordan form, right? This is not necessarily a 1 here. But we don't really need to have Jordan form. All we need is to have this new matrix represent a system that is back solvable. In other words, all we need is to have all zeros below the diagonal, and this always will be. So, pretty neat trick. So here's an example. So let's look at this one here. By the way, there's a homework question that's kind of analogous to this, where it's a 2x2 system. They come up with an example that involves a particle moving through space and velocity is a function of position, this kind of thing. So 2x2 system. If you go through and try to find the eigenvectors and eigenvalues, sadly, there's only one eigenvector. There is, as we like to say, a missing eigenvector. This matrix is not diagonalizable. You can't cite the theorem that we're very happy to write down in the last section. So what you do is, as described on the previous page, just take that eigenvector, supplement with, it doesn't matter, any old vector. Obviously, don't pick a multiple. It's any old vector that makes a basis, right? So, no particular reason I picked -1, 1, pretty arbitrarily. And this new basis will at least make your system back solvable. So, take this basis. Note that as your P matrix, right? There's P inverse. So this is your conjugation. Conjugating that original given matrix gives us this new form. Now, it's not Jordan form. Again, strictly speaking, to be Jordan form, this would have to be a 1, and it isn't. So, still don't care, right? Because it's upper triangular. Okay. And then, once you solve that, this can be back solved. Once you find your z's, then you substitute for the same argument. Okay. All right. How are we doing? Let's take a pause. Does anyone have any questions about this? Okay. All right. Let's see, how are we doing on space? Okay, wow, we are doing great here. I tell you what I'm going to do. A combination of considerations. One is this section is actually a little bit ahead of the other section. I don't know if I'm more long-winded in the later class or if they ask more questions, or I don't know what exactly. But I'm a little sort of too far ahead in this section. Also, we've covered more material today than I had really planned and more than we really need. So I'm going to cut it early today, and that'll give us a chance to catch up in the other class. See y'all later.